Good evening, Lamai. Right, today we are going to discuss about the titrations. Right, let's discuss what this titration means. Right, here actually we use the titrations, right, to come up with the number of moles of an analyte in an unknown solution. Right, so as this mentioned here, it is said titration is the procedure for determining the concentration of an analyte in a solution. Mainly for that we use the number of moles there at a solution of a known volume. Right, let's discuss how this thing is done. Right, let's consider, right, in a flask like this, right, you have an unknown solution. So this is an unknown solution, right? This is an unknown solution, right? Let's say there you have an analyte. You have an analyte here. Analyte. Let's say it is A. So let's say you are with 25 cubic centimeters of this solution, and you are supposed to come up with the concentration of this A in this unknown solution, right? That is your task, right? So we can come up with the concentration of this unknown solution, or we can come up with the concentration of this A if we are able to come up with the number of moles of A here. If we let's say it is X moles, if we are able to come up with this X, the number of moles of A in your solution here, you are able to come up with the concentration of A here, right? The procedure we use to find out this X, to find out this number of moles of your analyte in your unknown solution is referred to as the titration procedure, right? So let's discuss how to do this thing, right? To come up with the number of moles of A here, right? First, we use a solution called as standard solution. We use a solution called as standard solution. So normally, a standard solution is used inside a burette, inside a apparatus called burette. This kind of apparatus is there, referred to as the burette, right? Inside this apparatus, right, this burette, inside this apparatus, right, we'll come up with the standard solution, right? So if you have standard solution inside this, right, standard solution. We use standard solutions to find out the number of moles of analyte in your flask, right? So what is this? What is meant by a standard solution, right? Standard solution is a solution where we exactly know the concentration. Standard solution is a solution with a known concentration, with a known, with a known concentration. Right? Standard solution is a solution with a known concentration. Basically, we use a standard solution to find out the number of moles of the analyte in your flask. Right? How to use that? The procedure is done like this, right? Let's say this standard solution is B. Let's say the chemical there is B, right? Chemical there is B, right? Chemical in your analyte is A, right? We use B to come up with the moles of A here, right? So the idea is this, right? What we do is actually we will react this A and B. We will react this A and B, right? So to do that actually, right, we can open the tap here at the burette. We can open that tap here. So the solutions of the molecules of B will come to the flask, which is also known as the titration flask, right? So that when those two guys get in contact, they will react, right? Let's say that reaction occurs like this. The A will react, let's say 2 of A will react with B to give some products, C plus D as products. According to this equation, the reaction occurs. Let's assume that. So our main task is to come up with this X number of moles, right? If you know that moles, you can come up with the concentration of A, right? That is our major goal here, right? Okay. To find out that, we use a standard solution which is coming inside a burette, right? So what we do here is, first we open the tap of the burette, right? So that the solution B, right, which is known as standard solution, will come into the flask, and that will react with the A. That will react with the A, right? When the A, the analyte is totally consumed, when the analyte is totally consumed, we are supposed to stop the tap, right? When the analyte is totally consumed, we are supposed to stop the tap, right? Let's say when you have added 20 milliliters from the burette solution, the A is totally consumed. Then you have added 20 cubic centimeters from the burette solution. Let's consider that A is totally consumed, right? This guy's concentration is known, right? Known concentration, let's say it is as 0.1 mole. And what we have said is, when you have added 20 cubic centimeters from the burette solution, right, the A is consumed, so that we will stop the tap, right? So the calculation is done like this. So with the use of this data of the standard solution, right, with the use of that data of the standard solution, that means 0.1 mole, 20 cubic centimeters were consumed. With the use of this data, you can come up with the number of moles of B. You can come up with the number of moles of B, right? So if you know the number of moles of B, according to the equation, with the use of the stoichiometry, you can come up with the number of moles of A. Number of moles of A, right? That will be twice of this amount, twice of that amount. That is actually equal to your X. It's actually equal to your X, right? That is how we are supposed to calculate the number of moles of the unknown analyte in your titration flask, right? With the use of that, if you know the X, then you can come up with the concentration as the volume is known, right? That is how a titration is used to find out the number of moles of to find out the concentration of unknown or analyte solution in your flask, right? The idea is clear, right? So let's go to the things in your note. It says titration is a procedure for determining the concentration by mainly measuring the number of moles of analyte in a solution using another solution of unknown concentration, which is known as the standard solution. Using another solution, you're supposed to find out the concentration of an unknown, right, solution, right? So that is the procedure, right? So after that, it says to find out the completion of the reaction, which is also known as the endpoint, we use a chemical known as indicator. Usually indicate changes their color when the reaction completes. Let's discuss about that thing as well, right? So I had earlier told you what? When you have added 20 cubic centimeters of this burette solution, I had told you that the analyte completely reacts, right? So analyte completely reacted, so that we had stopped the tap. When we are to measure the volume consumed, it was 20 cubic centimeters, right? That was the practical situation. When the analyte completely reacts at the flask, we stop the tap. When we are seeing the reading of the burette there, it is said as 20 cubic centimeters. That is how we have found out the amount consumed from the burette solution to completely react the analyte solution, right? So basically, right, there should be an indication. There should be an indication, right, when the analyte totally consumes. There should be an indication when the analyte totally consumed to stop the tap. So we should know that the analyte is totally consumed. No? So because analyte is not going to shout that yes, I am completed, I am totally consumed. It is not going to shout like that, no, right? So there should be indication from the flask side, right, that the analyte is totally consumed or analyte is completely reacted. There should be indication. That indication is actually done by, right, a chemical called as indicator. A chemical called as indicator. So indicator, what indicators do is actually those will, right, do a color change in your solution at the flask, right, when the analyte completely ends. When the analyte completely ends, the indicator, that chemical, will change the color of the solution at the flask, right? So that, right, we can identify that the analyte is totally consumed, right? If you know, need to come up with a better idea about that thing, it is like this, Lama. So I'll, right, give you an idea there, right? It's like this. Say, right, you have a NaOH solution at the flask. Say you have NaOH solution at the flask, right? And you are coming up with 25 cubic centimeters of that thing, right? You're coming up with 25 cubic centimeters of NaOH, right? Your task is to find out the concentration of NaOH in this flask, right? Let's say, right, some simple example about a titration. So your task is to come up with the concentration of this NaOH in your flask. So that means your goal is to find out this number of moles here, right? So before starting the titration, right, we will add some chemical which is known as the indicator. Indicator chemical, right? So that, let's assume that indicator is going to give you a blue color when a base is there. Let's say this indicator gives you a blue color, right, when the NaOH is there. So you have the NaOH 25 cubic centimeters, right? So X moles are there, right? As you have added that indicator, it gives a blue color. Let's say it gives a blue color when the base is there, right? So your solution becomes blue, right? So the idea is you have an indicator in a basic solution, it gives a blue color. Let's say in a neutral solution or in an acidic solution or neutral solution, let's say it gives a red color or something. Such indicator is there, indicator chemical, right? So as you have added the indicator chemical here, now the solution is blue colored, right? Then you start the titration. With the use of a burette. This is your burette, right? This is your burette. Inside the burette, let's say you are with some H2SO4. You use this acid to react with the NaOH, right? With a known concentration, standard solution with a known concentration. This is how to copy this X. So what you do is, right, you open the tap, right, you open the tap to, right, provide the droplets of H2SO4 towards the titration flask, right? So the reaction will occur, right? So this reaction will happen, right? So your H2SO4, when you open the flask, when you open the tap of the burette, your H2SO4 molecules will react with NaOH to produce sodium sulfate and H2O, right? This reaction occurs, right? So after consuming all the NaOH, when all the NaOH is consumed, what will happen? When all the NaOH is consumed, when there is no longer NaOH appearing there, right? Only the sodium sulfate, so produced sodium sulfate and water is there, right? No longer the NaOH is available there. When that happens, the blue color will turn to red color. The blue color will turn to red color. When the reaction occurs, the NaOH will consume. No? When all the NaOH is consumed at the flask, at that point, only the sodium sulfate and the water is there. The so produced sodium sulfate and the water is there. No further, no longer NaOH is there at the flask. Then the flask, the solution of the flask will convert to red color, right? Then the solution of the flask will convert to red color, right? At that exact point, we will stop the tap. At that exact point, we will stop the tap. So we're supposed to stop the tap at that exact point, and then we can measure the amount of H2SO4 consumed there. Amount of H2SO4 consumed there can be measured with the use of burette, right? So let's say the burette reading is given as, burette reading is given as 30 cubic centimeters. So basically the idea is we stop the tap when the indicator changes its color. We stop the tap when the indicator is changing its color, right? That is the exact point where all the analyte solution, the analyte species, chemical species, totally reacted. When analyte totally reacts, the indicator will change the color. At that exact point, we stop the tap, right? Okay. After that, we can calculate the H2SO4 consumed. That number of moles will ultimately provide the NaOH at the flask, right? So we can use these values of H2SO4 ultimately to come up with the number of moles of NaOH. How come? So the NaOH is the thing to find out. The amount of H2SO4 consumed is actually this amount. So we can come up with this relationship. This is X moles. This is what we need to find out, right? So the H2SO4 amount is going to be half of that, as 2:1 ratio is there, right? So actually this value is equal to the number of moles provided by these numbers, right? So this is the data point. This is the data point. So we can copy the equation for that in terms of x. So we can solve for x here, right? If you're supposed to write, right, we can write like this, right? For number of moles of H2SO4, right, we can write the H2SO4 moles as 0.1 mole 30 cubic centimeters, no? 30 cubic centimeters. Right, that value is actually 3 into 10 minus 3. So actually that is equal to x over 2, no? That is equal to x over 2. With that you can copy the x, right? That is how we can use a titration procedure to find out the unknown, the number of moles of an unknown. So that x will ultimately lead you to the concentration of that thing, right? So this is a little example of titration procedure, and I think you had got an idea about how the indicator is also used, right? So the moment at this color change occur is referred to as the end point. The moment at which the color change occurs of the solution is referred to as the end point. That is where you end the titration. That is where you end the titration procedure. That is where you stop the tap. This is referred to as the end point, right? Referred to as the end point. End point. So end point color change here is from blue to red, from blue to red. When NaOH totally consumes, the solution becomes red. So end point color change is blue to red, right? No? So that is how a titration procedure is done, right? So I think you had got some idea about the titrations, right? Okay, let's go to the note, right? What else we should know about these things, right? Right. So there are two types of titrations. There are two types of titrations they are in available syllabus to study, right? So one is the redox titration, that number two is the acid-base titrations, right? Basically we'll discuss about acid-base titrations, right, in the unit 12, right? In this units basically we will totally concentrate on redox titrations, right? Okay, let's copy the redox titrations, right? Okay. Right, first we need to discuss about the K-mean of titrations. Under redox titration, first we are going to discuss about the K-mean of titrations. Titrations with use of acidic K-mean form, right? Let's discuss what is done here, right? As the note says, it is said like, here the analyte, the solution with the unknown concentration or the number of moles will be subjected to complete oxidation with acidic K-mean form. Here the analyte will be subject to total oxidation with acidic K-mean form, and they measure the volume of K-mean consumed, here's the number of moles of K-mean consumed to completely react with the analyte, right? That is what the note says. Let's copy some example to understand the procedure here, right? So let's copy this example, right? So titration of oxalates. Titration of oxalates using H plus KMnO4, right? So let's do this stuff. Right. So it's like this lemma, right? Think of a unknown solution or solution with oxalate ions, C2O4 2 minus ions, right, with a known volume. So you are supposed to come up with the concentration of C2O4 2 minus ions, right? You need to find out the concentration of C2O4 2 minus ion, right, with the use of a titration method, right? Okay, let's see how to use kind of a K-min of titration to come up with the concentration of this thing, right? So first of all, your idea is to come up with the number of moles here, right? If you are able to come up with the number of moles here, right, you can come up with the concentration, right? The idea is clear, right? For this, we can use a K-min of solution to titrate with this, right? So, right, to write this one, you can use a acidic K-min solution, right? So, right, we are going to use an acidic K-min solution to titrate with this, right? See, okay. So you have the K-min solution, 285 cubic centimeters. So let's acidify, right? As we are going to use a K-min-O4 from the urate, right? As what we need is acidic K-min-O4, we need to acidify the solution first of all, right? So now your solution is like this. You have the oxalate ions, right, and some acid as well, right? So X moles of oxalate is there, right? The idea is clear, right? By adding the acid, the volume will change, but still the X moles is there, right? Okay, you haven't added oxalate no, from the top, right? Okay, now we are going to titrate this thing with K-min-O4, right? Let's take K-min-O4 from the burette and let's titrate this solution, right? From here you are adding K-min-O4. So what is the color of the K-min-O4? What is the color of the K-min-O4? The color of the K-min-O4 is actually purple, right? The color of the K-min-O4 is purple. I'll write it in. I write that thing in purple, right? It's better. So color of the K-min-O4 is purple, right? What is the color of oxalate? It is colorless, right? Oxalate is without a color, right? So C2O4 2 minus is without a color, right? Right? Okay, so we use some known constraint of K-min-O4, right? So let's say its concentration is just 0.1. Right. When the K-min-O4 droplets are added to the solution containing H plus and the oxalate, to the solution containing H plus and the oxalate, right? There is a reaction. There is a reaction which will occur. Let's write the reaction as well. What is the reaction which will occur with the K-min-O4 and the oxalate? So it is the reaction in acidic medium where the MnO4 minus reacts with the C2O4 2 minus, no? Right? That's the reaction. So these two guys will react to form the Mn2 plus and CO2. You know how to write the reaction now, right? MnO4 minus always reduced to Mn2 plus and C2O4 always oxidizes to CO2, right? If you have to balance this stuff, right, first you need to do about 2 here, and you have 5 electron difference here, right, 2 electron difference there. So after balancing, this will become an equation like this. I just write the equation, right? So 16H pluses with 2 of MnO4 minuses reacts with oxalates, 5 of them, to come up with 2 of MnO2 pluses and this thing and 8 of H2O, right? According to this reaction, the reaction is local, right? So when the C2O4 minus amount ends at the flask, when the C2O4 minus, after reacting like this, at some instance, all the C2O4 minus, the X moles will consume no, at the flask, total reacts at the flask. No? At that situation, what will happen? At the situation, when all the C2O4 minus guys totally consumes at the flask, right? The flask is still colorless. This guy is colorless. And when all the C2O4 minus consumes, still the flask appears as colorless, right? With the addition of the next drop, of KMnO4, the addition of the next drop of the KMnO4, what will happen? With the addition of the next drop, after the C2O4 minus totally consumes, right? Addition of the next drop, right, will convert this solution to pink color, right, due to the presence of excessively added drop of KMnO4, due to the presence of excessively added drop of KMnO4, solution will looks like pink. Do you get the idea? Now the idea is, right, till the C2O4 minus ends, all the KMnO drops added from the top will be reacted this with the C2O4 minus, so that flask won't contain any KMnO4 particles until the C2O4 minus ends. Until the C2O4 minus ends at the flask, all the KMnO4 added from the top will be consumed from this reaction. So there won't be any KMnO4 particles appearing at the flask till the C2O4 minus ends. After the C2O4 minus ends, the next drop adding from the burette, right? You are adding some MnO4 minus drop from the burette. There is no C2O4 minus to react with the MnO4 minus then. After the C2O4 minus ends, there will be further longer no C2O4 minus molecules to react with the MnO4 minus, so that the excessively added drop of MnO4 minus will remain at the flask. So that is a purple colored drop, and it will diffuse through the flask to give you a pink color, That is why the solution will appear as pink when the excessively added KMnO drop remains there, right? The solution is pink then, right? Pink solution. So when that happens, when the solution converts to pink, we know that C2O4 minus is no longer available in your flask. So that is your endpoint. It gives you the indication. The color change will give you the indication that the analyte has been ended and that has been totally consumed. So at that point, we stop the tap. When that color change happens, we stop the tap, right? And then we can come up with the volume of KMnO4 consumed there. With the use of the burette, we can come up with that value. Right? Now we can get the value of KMnO4 consumed from burette. Right? Let's say it appears as 30 cubic centimeters. It appears as 30 cubic centimeters. Right? So now we can do the calculation to come up with the X moles. Then you can use that X moles to come up with the concentration of oxalates. Let's do the stuff, right? So when we stop the tap, the reading was given as 30 cubic centimeters. That means that is the consumed amount of KMnO4 to totally consume the C2O2 minus, total react with the C2O2 minus, right? Let's do the calculation now to come up with these X moles, right? So calculation can be done like this, right? So these X moles, so this is now X moles giving you for five portions. X is for 5 portions. We need such 2 portions. So what we need to do is to come up with the MnO4 minus amount is what we need to do is actually we need to divide the X by 5. Then that will give you for 1 portion. We need such 2 multiplied with 2. So this is the amount of KMnO4 consumed to totally react with oxalate, right? So our data point appears here. This is our data point. Always my titration reading is your data point. If you have a titration involving it with your calculation, always your titration reading is kind of a data point, right? So we can use that data point to calculate the X, right? So data point is regarding the KMnO4. So you can come up with a relationship for the number of moles of KMnO4 consumed, right? So we can write equation for moles of KMnO4. Moles, no? Right? So KMnO4 moles can be written as 0.1 molar into 30 cubic centimeters. In decimal cubes, it's 13 to the minus 3 dm cubes. So the value is 3 into the minus 3. Actually, that value is equal to 2x05. So that we can write 2x05 is equal to 3 into 10 to the power minus 3. Right? You can multiply this thing. 15 over 2 is 7.5. So x is equal to 7.5 then. Right? You can write x is equal to 7.5 into 10 to the power minus 3. Right? So we had done the calculation to find out the x. Right? So x is the number of moles of oxalate which was there at 25 cubic centimeters of the flask. 25 cubic centimeters of the volume, right? Of solution, right? So that we can come up with the concentrations of oxalate with use of this thing, right? So I'll do the calculation here. So we can come up with the concentration, right? So the concentration of C2O2 minus ions can be written as the number of moles is 7.5 into 10 to the minus 3, and that was inside 25 cubic centimeters. 25 into 10 to the minus 3 decimeter cubes. So that will give you a value like 0.3. That is how we are supposed to calculate the concentration of an unknown solution of oxalate with the use of a K-mean for titration. Right now? The idea is clear, no? Okay. So this is how we are using K-mean for titrations to come up with a concentration of unknown. Right? So that is the idea. Right? So now when some more things to be discussed here. So you can complete the note, Lamai. While completing the note, I'll discuss a few more points here. So when we are discussing about the K-mean of titrations, when discussing the K-mean of titrations, right? There is no foreign reagent. There is no foreign reagent added to do the color change at the end point. To do the color change at the end point, no foreign reagent is added. The color change is done by the same K-MnO4, which is a reactant, of your reaction, right? There is no foreign reagent is added to come up with the color change. Just one of the reactants had involved with the color change, responsible for the color change, right? In such a situation, such indicators are referred to as self-indicators. Such indicators are referred to as self-indicators. So here the K-MnO4 is referred to as a self-indicator for this titration. For all of the K-MnO titrations, K-MnO4 is referred to as a self-indicator, right? So let's write that thing is also. So here the indicator is K-MnO4. So it is referred to as a self-indicator. Right? And what about the color change at the end point? Color change at the end point? Color change at the end point can be referred to as colorless to pink. Colorless to pink. It is colorless to pink, right? Colorless to pink. That is the color change. For all the K-MnO titrations, right? Indicator is the K-MnO4, and the color change at the end point is always colorless to pink, right? Colorless to pink, right? So mention that thing as well with your notes, right? Okay. What is self-indicator? It's like when a reactant of the reaction is involving as an indicator as well. Then such indicator is referred to as a self-indicator. One of the reactants of your equation, reaction is responsible for the color change. Right, the color is appearing because of K-4, right? So such a thing is referred to as a self-indicator. So it's a self-indicator, right? So you can complete the note here about a K-4 titration. So any kind of a thing. So it can be the Fe2 plus here, right? Anything which can get oxidized, right? Can be used for these kind of titrations, K-4, right? Okay. So complete the note here. That is actually at the page number 26, right? And you can write these things at the page number 27 as well. Some space is there. So this is how we are supposed to come up with the concentration of oxalate ions, right? Just complete stuff. Right, Lama. Let's go to the next kind of titrations. Right, the iodometric titrations. Right, let's discuss about that thing as well. Right, so then we can discuss about some questions, some calculation stuff, right? Okay, this is about the iodometric titrations, right? So as name suggests, this is all about measuring iodine, iodometry, measuring iodine, right? So let's discuss how this kind of a process will be helpful to come up with a concentration of an unknown analyte in your solution, right? So at the first point it says, here the concentration of the analyte, the solution with unknown concentration of moles, will be found as below. Some example is given. Let's consider how this thing is done, right? So finding out the concentration of IO3 minus using an iodometric titration, right? That is what we are supposed to do here, right? Finding out the concentration of IO3 minus using an iodometric titration, right? So 2 steps to follow in this kind of procedure, right? We follow 2 steps, right? The first step is to react the analyte with some solution, with some excess solution of iodine containing excess solution, right, to produce I2, right? That is the first step in iodometric titrations. The first step is to react to analyte completely to produce I2. React to analyte completely to produce I2. That is the first step. And second step is then going to be the produced I2 will be measured with the use of sodium sulfate. Right? Those are the 2 steps to follow when considering iodometric titration. Let's write one by one. Right? The first step is, right, you can write like this. First, the analyte will be reacted with excess amount of I2. Right? This is the first step. Right? Step 1. Analyte will be reacted with here the analyte is your IO3 minus, right? That will be reacted with excess of I minus to produce I2, right? That is the first step, right? Produce I2. right? So producing I2 is the first step. This is very important. This is always done with atomic titrations. Then we will measure that I2. That is how the procedure is completed, right? So if you need an example, I write like this, right? See, you have the IO3 minus. Your task is to come up with the concentration of this thing, right? Let's say it is inside 25 cubic centimeters. So you are supposed to come up with the concentration of this thing, right? So you can take the number of moles here as x moles. If you are able to come up with the x moles, you are done, right? So what you are doing here is actually adding some excess of I minus. So you can add some excess of I minus. So to provide I minus, you can come up with the Ki, right? Ki will produce the I minus, give you the I minus, no? Right? Along with some acid to provide the acidity to do this redox reaction, right? Normally for redox reactions to be happen, right, you need to provide the oxidizing agent, producing agent, as well as the chemical which need to acidify or basify the medium, right? So you can come up with the acid as well, right? So those should be added in excess. H plus should be also added, right? Could be provided by HCl or something, right? Okay. Then what will happen now? When you add like this, right? This reaction with the Ki and the IO3 minus will occur. Basically, K plus won't involved in redox reactions. The I minus will react with the IO3 minus, right? So I'll write the reaction here, right? This kind of reaction will occur. You can balance this thing with use of redox techniques. IO3 minus will react with 5O5 minus with 6 of H pluses. I just write the reaction here, right? 3 of I2 and 3 of H2. This kind of reaction will occur when you want to mix these two guys, right? So you will produce I2. You will produce I2 with this kind of reaction, right? So I2 will be produced at the end of the first step. Right? Producing I2 is the most important stuff, right? So now you can think of number of moles of I2 there, right? Because this is x moles. As the two things are with 1 to 3 ratio, this is going to be 3x moles, right? So you have 3x here. Right? That is the end of the first step, right? Producing I2, right? Producing I2, right? After that, we are supposed to measure this I2. If you are able to measure this I2, that means 3x moles, you are done. If you know the 3x, that means you know the x. That means you know the concentration of IO3 minus, right? So second step is always to measure the I2, right? With the use of titration with the involving of sodium sulfate, right? This is the second step, right? Let's discuss the second step as well, right? Step number 2. Okay, step number 2. Step number 2 is actually the produce I2. then the produced I2 will be titrated with a standard solution of sodium thiosulfate, right? Standard solution of sodium thiosulfate in Na2H2O3. Right? Standard solution means you know the concentration here, right? You know the concentration of this thing, right? Okay. So with that, you are able to come up with the number of moles of Y2 there, right? Okay. Let's go to that procedure. Right? So produce I2 is there. So let's see. This is a flask containing I2. Right? You have the I2 here. You have 3x moles here, right? So that will be titrated with sodium thiosulfate, right? All this titration will be carried out with use of sodium thiosulfate, right? A known solution, a standard solution. Let's say its concentration is 0.1. It's a standard solution, that means a solution with known concentration, right? So this titration procedure is with some points to remember, right? Some special things are there with this titration procedure, right? So first, right, what will happen is, right, when you are titrating this thing, basically the I2 solution is kind of brownish color, right? The I2 solution is kind of brownish color, right? This thing is brown, no? Solution is brown, right? So you want to see that. Solution is brown, right? Okay, brownish solution. Okay, when you are adding the sodium thiosulfate, right, what happens is when the I2 consumes gradually, solution becomes yellow and ultimately very light yellow, which is also known as the straw color, right? When the solution appears as a straw color solution, right? When the solution appears as a straw color solution, the I2 amount is very less, is referred to as a straw color solution. Right, when the solution appears as a straw color solution, so at that point normally the I2 concentration is very low. The I2 concentration is at that point normally 10 to the power minus 5, kind of very low concentration, molar. When that situation occurs, right, you will add the indicator, you will add your indicator there, right? At that exact point, you will add your indicator, which is known as starch. For this titration, starch is used as your indicator, right? Starch is your indicator, right? So indicator will be added when the straw color appears with the titration flask, right? That will appear when the I2 amount of your flask is very, very low, right? After that straw color appears, you put the starch there, right? This starch is added to that straw color solution, right? The solution will turn to blue color, The solution will become blue colored due to the complex formation between the starch and the I2. So I2 starch complex will be formed here. Due to the formation of I2 starch complex, the solution become bluish. Right? Solution become bluish. When that happens, right? After that happens, you start the titration again. Right? Again, the titration will be done, right? The same sodium sulfate solution is used. Right? Actually, so that again the I2 will start to react with the sodium sulfate. Again, the I2 will start to react with the sodium sulfate, right? And when the I2 ends in your flask, what happens is actually only starch will appear here. That means it becomes colorless. The color of the starch is colorless actually, right? So when only the starch is appearing there, the solution becomes colorless. That happens when all the I2 is consumed by the sodium sulfate, right? So that is your endpoint. At that point, you just stop the tap. Right? So we can come up with the amount of sodium sulfate consumed till that moment after stopping the tap, right? You stop the tap, right? Let's assume the amount of sodium sulfate consumed there is actually 30 cubic centimeters. So you can use this data point. To proceed the calculation. Always titration reading is kind of a data point, right? Okay. So let's do the calculation then. So the reaction involving this procedure is what? The reaction involving this procedure is this, right? Sodium sulfate reacting with I2, basically 2 of sodium sulfate to react with I2 to produce 2 of NaI plus Na2S4O6. You should know this reaction by heart, right? This reaction involving the I2 titration, right? So as we know, the number of moles of I2 is 3x moles. Is this 3x, the same 3x here? The amount of sodium sulfate consumed, right? Here is going to be 6x. That will be equal to the amount given by these two numbers, right? So we can copy the right calculation with use of these numbers, right now. So Let's do the calculation here, right? Okay, for the calculation you can write for the moles of sodium thiosulfate, right? So Na2H2O3 moles is equal to, right, this amount 0.130 cubic centimeters. So 0.1 mole cubic centimeters, right? That value is going to be 3 into 10 to the power minus 3, right? Actually that value is equal to 6x, 6x, value is equal to 6x. So your 6x is equal to 3 into 10 to the power minus 3 moles. That will give you your x as 3 divided by 6 is 0.5, no? 0.5 into 10 to the power minus 3. This x means actually the IO3 minus amount, right? So now we can come up with the concentration of IO3 minus. So the concentration of IO3 minus is going to be the number of moles of IO3 minus divided by the volume, right, which was there in the solution, right? See, the volume we took is about 25 cubic centimeters, no? Right, 25. The x moles were inside 25 cubic centimeters, right? So you can use that thing to come up with the concentration of the IO3 minus, right? So these two things will cancel off, right? So giving you a 0.5 over 25, that means 2 over 100, that means 0.02. Right? That will be the concentration of IO3 minus according to this procedure. So you can use this kind of a calculation, titration, to come up with the concentration. Right? This is how a RWD titration is done. Right? So you can complete the note llama here. Right? So when it comes to RWD titrations, right? 2 steps are involving. Always first the analyte will be converted to I2, and analyte will be completely reacted to convert to I2. That is the first thing to do, right? After that, that I2 will be measured. That is why this is referred to as the RWD titration. Then the I2 will be measured with the use of a titration with the involvement of the sodium thiosulfate, right? So this is titration. So I'll write some more important stuff here, right? This titration, your indicator is starch. Your indicator is starch. Indicator of the titration is starch. Here, starch. And the endpoint color change is actually blue to colorless. When the solution appears colorless, we stop the tap. The endpoint color change is blue to colorless, right? It is blue to colorless. right? So write this thing as well, right? So just complete your notes there now, right? Okay, now let's do the question which is appearing at the page number 32, no? Yeah, at the page number 32, right? You can see some questions appearing with the rate of titrations as well as the additive titrations at the page number 33, right? Let's do those few questions of those, right? Okay, right. Let's start with the question number 12, right? So you can see the question appearing here. The sample X contains Fe and some other inert materials. To find out percentage of Fe in the sample X, following procedure was done. So it's a very simple question, right? 1 gram of the sample of X completely dissolved in diluted H2SO4 to convert all the Fe to Fe3 plus, right? Then the resultant solution was titrated, right? So with 1 mole MnO4 solution, endpoint was given. Let's see how to solve this one. So you had a sample, X contains Fe. So you have a sample. So let's say this is your sample, right? Right, it contains Fe. So Fe is also there in your sample. Some other stuff also there, right? So other inert material also there, right? Right. So the whole thing is done to calculate the percentage mass of Fe. So identifying the goal. So we can take the amount of moles of Fe as X moles. So identifying the goal, that is the first thing, right? So you can write let the Fe amount is equal to X moles, right? In how many grams of sample, right? 1 gram of sample, in 1 gram of sample, identifying the goal. So you have it 1 gram of sample, right? Right. Let's try to do the stuff here. So what they have done? First, 1 gram of sample was completely dissolved in W2H2SO4. Completely dissolved in W2H2SO4 to convert all the Fe to Fe2 plus. So this thing is dissolved, right? This is dissolved in H2SO4, right? So we can write dissolved in dilyl sulfuric to completely convert all the Fe to Fe2 plus. That is what they are saying. So then what will happen? Now you would come up with a solution. So sorry, I'll take some space here. Right? Then you would come up with a solution. With some Fe2 plus, right? To convert all the Fe to Fe2 plus, you had done this thing with the dill sulfuric, right? To convert all the Fe to Fe2 plus. So that Fe2 plus amount here is going to be X moles as well, right? As you had X moles here, Fe2 plus amount also should be X, because you had converted all the Fe to Fe2 plus with use of dill sulfuric, right? Okay, that is the first thing they are saying, right? Until the data point, just read the stuff, right? So after that, what they have done? Then the resultant solution was titrated with a 0.1 molar MnO4 minus. So this is titrated, right, with a 0.1 molar MnO4 minus solution. So MnO4 minus solution, the concentration was 0.1 molar. Titrated with a 0.1 molar MnO4 minus solution. Endpoint was observed at 25 cubic centimeters. Endpoint was observed at 25 cubic centimeters. That's what they are saying, right? So you clearly see the data point here. Your data point is very clear here. This is your data point, right? To completely react with the Fe2 plus, this amount of MnO4 minus was consumed, right? So first come up with the chemical equation, then we can write a simultaneous equation for the amount of MnO4 minus, right? So in this flask, you have H plus as well, right? In this flask, you have H plus as well, right? So you had added some H2SO4, right? H plus is also there, right? Okay, let's write the chemical equation first of all, right? So this is the chemical equation in acidic medium between the Fe2 plus and the MnO4 minus. You clearly know that MnO4 minus will reduce to Mn2 plus in acidic medium. In acidic medium, the MnO4 minus will reduce to Mn2 plus. So the reaction here is going to be MnO4 minus reacting with reacting with Fe2 plus to produce the Mn2 plus. Acidic medium MnO4 minus reduces to Mn2 plus and the Fe3 plus. No? Let's try to balance this one, right? So the manganese is with plus 7 oxygen state. This is with plus 5. So sorry, not the plus 5. It is plus 2, no? So the 5 electron difference here. This guy is plus 2. This is plus 3. 1 electron difference. So you need to multiply this thing with 1 and this thing with 5. So you need to come up with 5 here as well as here. Then H pluses to balance the charges. Minus 1 is there, plus 10 altogether, plus 9 is there as the net charge. Here you have plus 15, plus 17 as the net charge. So 8 units of difference, right? 8 units of difference. So you need to add some 8 H pluses, so that to balance the hydrogens you need to come with 4 of H2Os. No? There is a redox reaction possible here, right? I just erase this stuff, right? Right. So the amount of Fe2 plus is X moles. So our data point is with MnO4 minus, it is going to be XO5, no? XO5. right? No? This is x moles. X moles is for 5 portions. We need such 1 portion, right? X over 5. So now we can come up with the equation for the data point. So our data point is for the Mn of minus. So we can write the equation, right? For moles of Mn of minus, right? Moles of Mn of minus, you can write it is equal to 0.51 molar 25, no? 0.1 molar 25. That value is actually 2.5 into 10 to the power minus 3. That is equal to x over 5. It is equal to x over 5. Right now, this is equal to x over 5. So x over 5. So I write it here. So we can write x over 5 is equal to 2.5 into 10 to the power minus 3. Right now, number of moles of Mn of minus is x over 5, right? So x is equal to this thing into 5, that is 12.5 into 10 to the power minus 3, right? So the value of x is 12.5 into 10 to the power minus 3. So as we know the x, right? So now we can copy the mass of the Fe, right? So that will lead you to the percentage of Fe, right now. Okay, so x is found. So you can copy the mass of Fe. Right, mass of Fe, right, 12.5 into 10 to the power minus 3 is the number of moles of Fe that needed to be multiplied by its g mole minus 1 value, which is 56 here, right? So the mass of Fe is given as, let's do the calculation, 12.5 into 56, no? So that value is 700, that means 0.7. 10 to the minus 3 is also there, grams. So now we can compute the mass percentage. So you have 0.7 grams. Total mass is 1 gram, right? 1 gram into 100%, right? So your amount will be given as 70%. Right now, that is how we are supposed to solve this kind of question. Very easy one, right? So actually, we had used the titration to come up with the moles of Fe there, right now. So you can complete the stuff here, right? Right, let's go towards the next question now. Question number 13, right? Okay. So we have the question number 13 here. Right. Let's try to solve this one. Right. So you see, a solid sample is there, right? You have a solid sample contains KCl and inert materials, right? You have solid sample, right? So you have solid sample here, right? Some inert stuff are there, as well as KCl. Some KCl is also there, right? To find out the percentage of KCl in the sample, the following procedure was done. So our goal is to find out the percentage of KCl there. So identify the goal. The X-mos should be with the KCl then. Right? Okay. 3 grams of sample was completely dissolved with W-H2SO4. Okay, let's do this stuff, right? So 3 grams of sample was completely dissolved with H2SO4. Right? So what will happen then? So the K plus the KCl comes to the solution. Right? So the K plus and Cl minus, no? Right? And sulfuric also there, no? So medium is acidic, right? Acid will also appear there, right? The number of moles, so number of moles of KCl is still the same. That won't change with the addition of H2SO4. The number of moles of KCl won't change, right? So anyway, the H plus is also there in the solution, right? Acidic solution is there, right? Acidic solution is there. So it says 3 grams of sample was completely dissolved with the W-H2SO4 and titrated using 0.1 molar K2Cr2O7. So that is titrated using K2Cr2O7, 0.1 molar solution, the standard solution. The concentration is known, right? And they are saying the burette reading at the end point was 20 cubic centimeters. At the end point, the burette reading was 20 cubic centimeters, right? Okay. So that is your data point, right? That is your data point actually. This is your data point. Always titration reading is kind of a data point, right? Let's try to come up with the chemical equation first. Then that can be used to come up with the simultaneous equation for this data point, right? First use the let's come up with the chemical equation, right? Okay. See, first we need to identify the reactions which will occur. So K plus won't have anything to do here as well, right? K plus won't involve in the reactions, right? So that is why I just erase the K plus there, right? So the Cl minus and this dichromate. So you have the dichromate ions here. So in acidic medium, what will happen to the dichromates? In acidic medium, dichromates will reduce to Cl3 plus, right? Dichromates will reduce to Cl3 plus, right? It's a reduction, right? The idea is clear, no? This is plus, 3, this is plus 6, right? It's kind of reduction. So we would observe some oxidation at the flask. Think of oxidation at the flask. So what should happen to the Cl minus then? Right? The Cl minus, we know the X minus form of the X2 form. It will get oxidized to X2 form, Cl2. Right? So it's a kind of a oxidation towards the zero oxygen state coming from the minus 1. Right? No? Okay. Let's try the reaction then. Let's come up with the balanced chemical equation, right? So that is the equation between the dichromate and Cl minus. Reaction between the dichromate and Cl minus. Let's write in acidic medium, right? Cr2072 minus reacting with Cl minus to produce Cr3 plus and the Cl2. Let's balance this stuff. First of all, you need to come up with 2 here, right? For 2 of chromiums and 2 here as well. Then let's balance the stuff, right? So the summation of oxygen state here is going to be plus 12 minus 14 plus 14 minus 2 is plus 12. This is 2 into plus 3 is plus 6. So difference is 6 units. This minus 1 into is minus 2. This is 0. So difference is 2 units. So you need to multiply this thing with 1 while this thing with 3. No? So multiplying this thing with 3 means this becomes 3 and 2 into 3 becomes 6. No? So that becomes 6. Right? Now it's time to balance the charges of both sides. Minus 2 minus 6 is there, minus 8. Here plus 6. So 14 units of difference. So you can come up with 14 H pluses here. And to balance the hydrogen, you need 7 H2Os. Right? So let's erase this stuff, right? No need of these things now. Right, that is our equation. So let's come towards the data point. Right, here the number of moles of Cl minus is known as the X moles. That is our goal. So our data point is with the dichromate. So if this is X moles, this becomes XO6 moles. XO6, right? No? XO6, right? So now we can come up with our simultaneous equations, right? So that will be written for your data point, which is the amount of dichromate, right? Let's write the equation for amount of dichromate, right? So we can write, right, for the moles of dichromate, no? Sorry. For moles of K2Cr2O7, right? So K2Cr2O7 moles equals to, the concentration is 0.1, volume is 20. So the value is 2 into 10 to minus 3. The value is 2 into 10 to minus 3, right? So that is equal to x over 6. That is equal to x over 6, right? 2 into 10 to minus 3 is equal to x over 6. So two into 10 to minus 3, no? Right? X over 6 is equal to 2 into 10 to minus 3, right now? Okay. So your x is equal to 2 into 10 to minus 3 moles, right? X is the number of moles of KCl, right? X is the number of moles of KCl here, right? So then we can come up with the weight of KCl, no? Come up with the mass of KCl. To find out the percentage mass, you need to come up with the mass of KCl, right? So the mass of KCl going to be equal to its number of moles should be multiplied with its G mole minus 1 value, right? Should be multiplied with its G mole minus 1 value. Then you get the grams, right? What is the G mole minus 1 value? You have 35.5 here, you have 39 here. 39 into 35, 39 plus 35.5. The summation is going to be 74.5. Right? So let's multiply the numbers. 12 into 74.5. That will give you some 3 decimals should be also there. So 0.894 grams. Right? So this is the mass of KCl. So now we can come up with the percentage. So percentage is 0.894 grams divided by, we have 3 grams there, no? Right? So let's divide that thing with 3. So it is going to be 29.8, no? And this is how the answer looks like, right? So values are okay, no? .1 20, right now. So the number is 29.8, right? So that is how we are supposed to balance the stuff, right? Balancing is correct, right? So number of moles of dichromate is equal to x over 6 here with this balancing, right? So that is equal to 2 into 10 minus 3. So x over 6 is equal to 2 into 10 minus 3, right? So that x is the number of moles of KCl. So you can copy the mass of KCl by multiplying the number of moles with the G mole minus 1 value. That will give you this value as your number, right? Grams. So this goes inside 3 grams of the sample. So your KCl value becomes ultimately 29.8 the percentage, right? Okay, let's complete the outline. Now just do the question number 13 and 14, right? Sorry, we had done the 13, right? Just do the 14 and 15 as homework, right? So let's discuss about the question number 16 and 17 as well, right? Let's quickly come up with the question number 16 here, right? Right, here the question number 16 regarding kind of a volumetric titration, right? So let's try to solve this one. Right. Okay, see what they are saying. So this is to find out the percentage of Fe in solid sample X, the following procedure was done. So 2 grams of the sample X was dissolved in conc H2SO4 to convert all the Fe to Fe3+, right? So it's like this. You had a sample, right? You took 2 grams of the sample. To find out the Fe percentage, you had done this procedure, right? Some other stuff is also there. That is why you need to copy the percentage here. If not, you can take it as the 100%, right? So there should be other stuff as well. Right? You can take the amount of moles of Fe as X moles here. That is your goal, right? So you can write that thing. Let Fe amount is equal to X moles in 2 grams of the sample. Right. Let's try to do the stuff, right? So what they have done. First, 2 grams of sample X was dissolved in concentrated H2SO4 to convert all the Fe to Fe2+. Right. So what they have done, they have dissolved this thing. Consider H2SO4 to convert all the Fe to Fe3+ here, right? So now you are with a solution containing Fe3+. Fe3+ is there. So amount of moles should be X moles. So you haven't added any Fe from outside, right? You haven't added any Fe from outside. All the Fe is converted to Fe3+. That is what they have said, right? Convert all the Fe to Fe3+. So the Fe3+ amount should be also X moles, right? Okay. So that is done. So you are with acidic solution, right? Keep that in mind as well, right? So you have the acid as well here, right? So this is acidic. It's acidic medium reaction which is to occur here, right? So the resultant solution was neutralized. They have neutralized. The solution was neutralized. That means, right, this is neutralized. So H plus neutralized, right? So we can write that thing as well. Dissolved in H2SO, then neutralized. So you will come up with this kind of solution, right? Then what they have done. The excess of Ki solution was added. Then you have added excess Ki solution. Solution was added. And the resultant I2 was titrated. Then they are saying the resultant solution contained I2. Definitely, I minus form should convert towards I2, right? So the I2 was titrated with sodium thiosulfate. That is what they are saying, right? They are saying excess Ki is added. The resultant I2 was titrated with sodium thiosulfate. The concentration is given as 1 molar for sodium thiosulfate. And the amount consumed, the volume consumed is given as 20 cubic centimeters. So a titration reading is made again. So you can say that is your data point, right? So data point. Until you meet a data point, just go to the right. Just go to the question, right? When you have met the data point, just stop from there and complete the calculation up to there, right? So this is what they have given, right? So they have asked you to come up with the color change at the end point, right? You know the color change at the end point, right? The color change at the end point for a aluminum titration is actually blue to colorless. The color change here is blue to colorless. You can write that thing, right? The answer for the from number 1, color change. At end point, always for aluminum titrations it is blue to colorless, right? This done. So then write the balance ionic equation and then the achieving the goal, right? So let's write the equations related to this thing, right? First of all, you have to choose the reactions which are to occur here, right? Just try to come up with those, right? So first thing, K plus is no need, no use, right? So I minus here will convert to I2. Converting I minus to I2 is kind of a oxidation. It's kind of oxidation. -1 going to a 0. So there should be a reduction at the flask. So what will happen? The Fe3 plus will reduce to Fe2 plus. So this one will reduce to Fe2 plus there, right? That is your reaction there, right? Here the reaction is I minus will react with the Fe3 plus to produce I2 and the Fe2 plus. Let's complete that reaction now. First of all, your I minus Fe3 plus reaction, right? Fe3 plus reacting with I minus to produce what? Fe2 plus and I2. Let's put the numbers here. So between these two guys, only 1 electron difference among these two. First of all, you need to come up with 2 here. Redox atom balancing. Then between these two guys, -1 minus 2 appears here, 0 appears here. So 2 electron difference. So you need to multiply this thing with 2, no? This with 1. So multiplying this thing with 2 means you have two things here. The charge balancing plus 6 minus 2 is plus 4. Here it is plus 4, no? Things are balanced, no? Plus 6 plus 4 plus things are balanced, right? So we can erase the unwanted stuff now. Right? And the second equation for this thing is the additive titration, right? The relation between the I2 and the sodium thiosulfate, right? So that is 2 of Na2S2O3 reacting with I2 to produce 2 of NaI and the Na2S4O6, right? Now let's complete the stuff, right? So these are the chemical equations possible. Now we need to copy the data point. Right? So data point is with the sodium thiosulfate. So you have to bring this X towards the sodium thiosulfate here, right? So you have the X here. So that will produce X over 2 moles of I2, because it is 2 to 1 ratio, X over 2 moles of I2. So this produced amount is X over 2. So that X over 2 moles of I2 then will be titrated with the sodium thiosulfate. So that amount is then going to be X moles, right? So 1 to 2 ratio, X over 2 moles of I2 means it is X moles of sodium thiosulfate, right? So this is your data point, that X moles will be equal to the number of moles given by these two numbers, right? So that you can solve for X, right? Let's compute that thing, right? For the number of moles of sodium thiosulfate, that is your data point, right? For moles of Na2S2O3, the concentration is 1 molar. Concentration is 1 molar. Volume consumed is 20. So the number is 20 cubic centimeters, no? So we can't apply the cubic centimeters values, right? So it should be in cubic decimeters. We need to write, right? So 20 into 10 to the power minus 3 cubic decimeters. So the value is 20 into minus 3 moles. Right? That value is equal to the amount given here, equal to X moles. So your X is equal to 20 into minus 3. So yes, we have found out the amount of moles of Fe. So what we need is the mass. So mass of Fe is going to be number of moles into its molar weight. It is 56. Then the value is 56 into 2 is 112, right? So it is going to be 112 with another 0, right? So 3 decimals, right? So 1.12 grams, right? So now we can copy the mass percentage. That is 1.12 grams divided by the total weight, that is 2 grams. into 100, right? That value will be given as, this is just 0.56, so that is equal to 56%, right? No, so that is how we are supposed to solve this kind of a question, right? So let's complete this stuff now. Let's do the question number 17, right? Okay. Right. We are going towards question number 17, right? Okay. Let's do the stuff. See what they are saying. To find out the concentrations of SO3 2- ions in an analyte solution, the following procedure was done, right? See, so our goal is to come up with the sulfate concentration. So we can take the sulfate amount as X moles. So you can write let sulfite amount as X moles, right, in 25 cubic centimeters, right, in 25 cubic centimeter sample, right? So let's come up with a little picture there, right? You took 25 cubic centimeter solution, right? There you have sulfite ions, right, X moles. So what they have done, to a 25 cubic centimeters of analyzed solution, excess of KiO3 acidified with dilyl H2SO4 was added, right? So they have added excess KiO3, that means K plus and IO3 minus, right, with what? Plus acidity dilyl H2SO4. Dilyl H2SO4 is applied to acidify the solution, right, to provide H pluses, right? Then the liberated I2 was then titrated with sodium thiosulfate, right? So then liberated I2, definitely I2 will produce here, the IO3 minus will produce the I2, right? That liberated I2 was then titrated with a sodium thiosulfate solution. That guy is with a 0.4 mole concentration, right? Right, and the consumed amount is given as 20 cubic centimeters, right? Definitely we have a data titration there, so that is going to be your data point, right? Right. Let's try to complete the reactions here, right, and come up with the balanced chemical reactions, and then we can discuss about the simultaneous equation as well, right? Okay. So first thing, coming up with the equations here, chemical reactions here, right? So K plus won't involve in the reaction, redox reactions, right? So delta H2SO4, right? So H pluses and SO4 minus. So SO4 minus won't involve in redox reactions, right? So H plus is used to acidify the medium. Here H plus is used to acidify the medium, right? So the IO3 minus is the one to participate in the redox reaction here. So IO3 minus will produce the I2, right? X minus form or the X2 forms are the possibilities, right? So as IO3 minus is with plus 5 oxygen state of iodine, right? It will reduce to 0 oxygen state, right? So starting from the plus 5, if you think of 0 and minus 1, the X2 form and the X minus form, the easier stuff is to copy the X2 form first of all, right? To the closest oxygen state, it will get reduced, right? So the I2 is the possibility there. It is referred to as a reduction here. Decreasement of oxygen states, right? It's a reduction, right? So with this one, you should think of a oxidation at the flask. This is a reduction. This should be an oxidation, right? So let's write the reaction there first of all. So it's a reaction between the IO3 minus and the SO32 minus, right? So IO3 minus reacting with the SO32 minus to produce what? IO3 minus will reduce to I2, while SO32 minus will oxidize to SO42 minus, right? SO42 minus, right? It's clear, no? The closest oxygen state, it will get oxidized, right? Just balance the stuff, right? First of all, you need to come with 2 here, redox atom balancing. So you have 2 of plus 5 iodines, that is plus 10. It is 0. So you would observe kind of 10 electron difference. What about these two? Plus 4 appearing here, plus 6 here. So you would observe 2 electron difference. So you need to multiply this thing with 5. This thing with 1, right? Okay, no? Right? The thing is clear. Now we need to balance the charges. Minus 2, minus 12, minus 10 is there, minus 12. So here, minus 10. So 2 units of difference. So 2 of H plus is needed. So 1 H2O molecule is needed to this side, right? So that is how we are supposed to balance the equation there. Let's remove these things, run more stuff, right? Right, no? So that is the first equation, right? So then the additive titration equation. So that is the relation between the Na2S2O3 and the I2, right? So 2 of Na2S2O3 reacting with I2 to produce 2 of NaI plus Na2S4O6, no? Right. These are the 2 balanced ionic equations. That is done. That step is done. Now we need to come up with the simultaneous equation, right, for the data point. Right. So our data point is given with the sodium thiosulfate. So we have to bring this x value, which was with which is actually with the sulfite towards the data point, which is the sodium thiosulfate, right? Okay. So this is x moles. So that will produce, right, XO5 moles of I2, because those two guys are 5 to 1 ratio. So this thing will produce, the first reaction will produce XO5 moles of I2, right? So XO5 moles of I2 means the thiazolate amount is twice of that. That is going to be 2xO5. 2xO5. So that 2xO5 will be equal to the number of moles given by these two numbers, right? So that is our data point, right? Let's complete that thing. For the number of moles of sodium thiosulfate, right? So number of moles can be calculated by multiplying the concentration with the volume. So concentration is given as 0.4. Volume is given as in pointers of the 20 cubic centimeters. No? 20 cubic centimeters, you need to come up with cubic decimeters. So the value is then going to be 8, no? 8 into 10 to the minus 3, no? Right? So that value is equal to 2xO5, right? No? Equal to 2xO5. So 2xO5 is equal to 8 into 10 to the minus 3. So your x is going to be 40 divided by 2 is 20. 20 into minus 3, right? That x is the number of moles of your gold, that is SO32 minus, right? So that we can come up with the concentration of SO32 minus by dividing the number of moles of SO32 minus by its volume. What was the volume? It was 25 cubic centimeters. Right? Okay. So that this value becomes 20 over 25. 10 to the minus 3 will cancel off, no? 20 into 25 means 80 over 100, that is 0.8. Right, no? That is how you are supposed to solve this question, right? Now you can complete the note. Right. Son. Right, with this one we'll wind up for today's session, right? So actually we had done the titration stuff today and we had done some simple calculations as well. So as homework you can do the question number 14 and 15 appearing in your page number 32 and 33, right? Do those as homework, and you can try the next questions appearing at your page number 34 as well. Those are complex calculation questions, right? You can try those as well, right? So let's meet with the next session with the, actually we had not done the page number 28 yet, right? We'll meet with that thing about the chemical formulae next week. Until then, goodbye.